comes next in the sequence 1, 3, 5, 7, 9. Oops, I said that. Darn it. 9. Okay, that one was easy. Good, I gave away the easy one. So how would you describe that pattern? Odd numbers? Anybody else describe it differently than just like the list of odd numbers? Oh, you're going up by 2, add 2, something like that. So what we're going to find is there's like sometimes multiple ways to describe the same pattern. Okay, and that's something that I want you to focus on today is like how in words you can describe patterns. Okay, I'm not going to give this one away. So I'm going to say 2, 4, 8, 16, 32. How did you describe that pattern? Okay, you're doubling it. Anybody else say it differently?
They're all exponents of 2.
Okay, exponents of 2, and I often call those powers of 2. So it's like 2 to the first, 2 squared, 2 cubed, 2 to the fourth, 2 to the fifth. So the next one's going to be 2 to the sixth, so on and so on, right? Did anybody else say anything else? Double, exponents of 2. Yes, compounding on itself, and how do you mean that? Yes, okay, so doubling, sure. I would say the other thing I would expect to hear would be like multiplied by 2. Right? That's what you're doing to get to the next term. Okay, did anybody get the next term for 1, 4, 9, 16?
25.
Sierra? 25. And tell me how you describe that pattern or how you thought about that pattern, because there's multiple ways to describe this one too. Okay, those are the perfect squares, right? 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. Lexi, did you see that pattern differently?
I got 24.
How did you get 24?
Because I did 1, so I related it to the first one.
Uh-huh.
1 plus 3 is 4, 4 plus 5 is 9, 9 plus 6, or 9 plus 7 is 16, and then 16 plus 8 is 9, so 25. Never mind.
Okay, but that's the other pattern. So you can also see like what we would expect with Lexi's pattern, the next one to be plus 11, which will get us to 36, which is Sierra's next number if she's doing perfect squares, right? This is a really awesome thing to kind of just like keep in the back of your mind that if you see that pattern where it's going up by 3, 5, 7, 9, so it's not going up by the same number each time, it's increasing odd numbers. This sort of pattern always makes me think about perfect squares. That's the list of numbers that does that. Okay, those are the perfect squares. Okay, and the last one. 1, 1, 2, 3, 5, 8. Logan, what'd you say for that?
13.
13. How'd you get your number 13?
Because 0 plus 1 is 1. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 5 plus 3 is 8. And 8 plus 5 is 13.
Yeah, I have a hard time writing this when I'm listening. Something like that. So, can you describe in words why you're adding those particular numbers? 1 plus 1, 2 plus 1, 2 plus 3. Well, like, what's another way to describe it? Like, how would you say to the person the pattern when you don't know the two numbers?
Isn't it kind of like Pascal's triangle?
Let's just for a moment focus on like how else could you describe that more
You
generally?
add the number with the number before it.
Okay, add the number with its preceding number to get the next term. So a lot of times this pattern is described as adding the two previous numbers. Like if I want the next number, like so we have this blank, well let's do the next number after 13. If I want the next number after 13, I have to add the two previous numbers. 13 plus 8 is 21. Okay. Does anybody know the name of this sequence? Yes. Fibonacci. Now, I don't know if there's a relation to the Fibonacci numbers in Pascal's triangle. That would be something really interesting to look at. And I like the Fibonacci sequence as much as I like Pascal's triangle, which is a lot, right? It's so cool. There's so many cool things. So I'll try to find some little ways for us to plug the Fibonacci sequence in throughout our sequence and series unit because there is some really cool stuff. Fibonacci shows up like all the time in nature, so that's why I think it's so cool. Okay. I got a cool video too to go with that. We'll see. Okay, get out your notebooks. We're going to be talking about sequences and series. We got the right mindset now.
Yeah, let's go.
This month.
Enjoy snow day number 8. TLC.
Go ahead and walk these.
Okay. So, in relation to that last sequence we just talked about, I've got that flower that'll be my like icon for the whole chapter. You know, I just put a little picture on there to jazz it up. So I put that flower on there because hopefully I'll be able to get a chance to talk about how we can see Fibonacci numbers in things like flowers. So if you're dying to know what all this Fibonacci stuff is, you don't have to Google it. Okay, but we'll talk about it randomly. And Lex, you should go home and Google Fibonacci and Pascal and see if there's any kind of pattern in there. I don't know. If you look at your gold sheet, this is a short chapter. It's only 2 weeks long. So we're going to be testing over sequence and series next Friday. We are quizzing this Friday over the first 3 sections. Notice that this week we're on block schedules. So I'm going to see you today, tomorrow, and Wednesday. I won't see you on Thursday, and then you'll have a quiz on Friday. So we'll do a little bit of review in class on Thursday after our notes. And then you'll kind of need to do your own review outside of class so you're prepared for that quiz on Friday. The way I've set up our notes is, if you look at the gold sheet, we're basically doing the 3 sections 2 times. So this week we're going to do 8-1, 8-2, 8-3 quiz, and it's going to be all about sequences. And next week we're going to go back and we're going to repeat 8-1, 8-2, 8-3, but it's going to be all about series, and we're going to add in 8-4. Okay, so just so you know, this week is focused on sequences, next week is focused on series. They're related but different. Okay, so a sequence is an ordered list of numbers. Mathematical, of course, I gave you those brain teasers where the sequence was some kind of letter, and probably back in kindergarten, you looked at sequences that were like shapes or like colored things. Okay, yeah. So you've been doing sequences for a really long time, and you're really good at them. Just remember that. Now, another phrase for ordered lists that I like to use when I'm talking about sequences is it's really just a pattern. Like, it matters what order the letters or the numbers come because they have to be in that ordered list. They have to be in that pattern. And then each individual number in the sequence, just in terms of vocabulary, I call those terms. So like in the Fibonacci sequence, 1, 1, 2, 3, 5, 8, those are the terms in the Fibonacci sequence. Now, every sequence can be defined one of 2 ways. It can be classified as a finite sequence or an infinite sequence. A finite sequence is a sequence where you have a limited number of terms, so it has a last term, and that's just like whoever decided on that problem or that sequence just said, stop here. Okay. So I'll put up a finite sequence. I'm going to make it a really easy sequence to write down. How about 1, 2, 3, 4, 5? That's a sequence. And it has the last term. 5 is the last term. Now, how do I tell the difference between a sequence that's finite, where I should end at 5, and a sequence where it's infinite, it keeps going? That's going to be what we saw on the previous slide. After 5, we put a dot, dot, dot. Yeah. So it's just saying, keep going, 6, 7, 8, 9, 10. And sometimes you might have a finite sequence where you have more than just the 5 terms and you don't want to write them all out. So we could also do a like 1, 2, 3, 4, ... and we could say go up to 40, right? That would still be finite because it has the last term. But if it's left open there, that's infinite. Can't count the number of terms. Now, well, I mentioned that in this set of notes only because like later on we may be able to do, when we do series, we can do some stuff with finite series and some we can't do with infinite series. So it'll kind of depend on which form we have. Okay, I'm going to move this so you can see all 3 of these at the same time. But I want you can work with your pod members here. I've got 3 sequences. And I want you to do similar to like what we did in the warm-up. I want you to go ahead and work on describing the pattern and predicting the next term. I will say that, like, generally I think people are really good at saying what the next term is, and we have a harder time saying generally how to get that next term. So that's what I want you to focus on with your pod members is if you were trying to get someone to write down this sequence, what would you describe to them to get them to write the correct numbers? Okay. So, like, describe it in your own words. What's the pattern? How are you getting to the next number? Okay, I'll give you some time to kind of look at those. Can you take what you need and then put that away? Because I'm not going to listen to that rolling around all day. Distracts me. Not you. The candies or whatever. It's like a chip bag. Did you guys hear me? Take what you need and put it away because I'm not going to have to listen to those things go around all day. Miss Mark gets easily distracted. You're describing the pattern that you see and you're predicting the next term like we did in the warm-ups.
So, like, for that last one, so next year, say next.
Yes, I could ask that. There will be questions where I ask for the next term. There'll be questions where I ask for the 20th term. There'll be questions where I ask for the first 5 terms. I can ask for anything. You guys are quiet. Are you talking to your pod mates, making sure you got patterns?
See.
You can describe? Get the next term?
The last one, it's like the positive one.
I did Iowa too.
What is the next one? Like the
1860
Okay, sounds like we're ready to discuss.
16 plus.
Okay. Raise your hand if your group can describe to us how to get to the next term for 2, 6, 10, 14. TJ, what did your group say?
Add 4 to the previous term.
Add 4. And you can say to the previous term, but I'm just going to write add 4, right? Okay, and then what is your next term?
18.
18. Okay. New group. Describe to us the pattern. Josh?
I said add 1 to the denominator.
Add 1 in the denominator.
Like what?
What would you say about your numerator for pattern? Keep numerator. Okay, so that's the reason why I wanted to ask you about both of those is if you see something that's a fraction and like the numerator and the denominator are changing or staying the same differently, then describe both, right? So that the person knows if they're trying to create this pattern, they're always going to keep 1 in the numerator. Okay, so they know what that is, and then the denominator is changing up by 1. So what was your next term? 1/8. Okay. And the last one, 1, -1, 3, -3, 5. I'd say most people find it really easy to tell me what the next number is, right? -5. So how did we describe the pattern? Lexi.
I just said subtract double of the number to get your next number. So like 1 minus 2 is -1. 3 minus 6 is -3. 5 minus 10 is -5.
Okay, and then that works from for 2 numbers, but what about the pattern, like how do you get from -1 to 3? How do you get from 3 to 5, right? So I mean I see that pattern. I get what you're saying there. I would agree with that.
I said positive, negative flipping, going up by odd numbers.
Okay, alternate positive or negative, and you said flip, but I'm just gonna write alternate. That means change. Alternate positive and negative. And you said up by odds?
Yep.
So how do I know that I wouldn't write 1, -3, 5, -7? You know? I mean, that fits that description too. Yeah?
A positive, and then it's opposite, and then it's all odd numbers.
Okay. So maybe we're going to change it. We're going to say a positive and its opposite. For all odd numbers. That's what you said, right?
In increasing order.
In increasing order. Okay, so if I asked you, what's the first positive odd number, you'd say 1. And then its opposite is
-1.
-1. And now I'm doing it for all odd numbers in increasing order, so I do 3 and -3 and 5 and -5. Yeah, I think your description is okay. I would maybe say alternate positive and negative for the odds, like repeating the odd, or positive and negative for each odd number, something so that you're gonna repeat that number. Okay. Now I will say. Okay, I will say that. The way, in terms of describing those patterns, it got more difficult as we went down, right? Some patterns are going to be real basic, real easy. Okay. Some, like a fraction, maybe I got to talk about a numerator and a denominator. And then this last one, it's a little bit trickier to think about. If I described that to somebody who wasn't in this class, would they actually write down the numbers that I'm asking them to write down? Okay, so that, thinking about that. And I'll say this. The harder it is for you to describe the pattern, generally the harder it is to write the rule. Okay, but there are some easy patterns that maybe coming up with a rule can be tricky. So when you're doing your homework tonight, be aware there's a set of problems right in the middle of that homework where you gotta shut off your phone, shut off your TV, shut off your music, and you gotta sit and think. And you gotta try some things, and it might not work, and so you switch it around and you try something new, and you hope that you can find the pattern that works. But this last one, I'm not gonna have us write a rule. We would need some kind of function that we don't yet have, knowledge of, to be able to actually write a rule for this. We could probably write rules for the first two, and we're gonna come back and look at that. But know that, on your homework assignment, it's always going to be something I expect you to be able to figure out if you thought long and hard about it. So don't always think that you're going to get it on the first try. You might write a rule and then you wrote a bad rule. So you try writing a new rule. Okay, so I keep using this phrase rule, so I need to start talking about that. We're going to switch over momentarily to sequence notation and rules. Sequence notation is a lot like I have over here on the sideboard. Algebra 1, I think you get introduced to function notation f of x. Just a fancy way to write y. And then in probability, I gave you a new notation for probability, p of a. So the probability of event A. And now I'm talking about sequence notation. It doesn't use the parentheses for that second variable, your input. It uses like a subscript. So that n is lower than the regular line of text and it's smaller. So when I talk, I just want you to make sure that you like understand what I'm saying. A sub n. Right? That's what I'm describing it as, a sub n. When I say it really fast and then I think people never know what I'm saying. A sub n. This a sub n right here, this means the nth term in the sequence. So I've got some examples where I put in different numbers for n. I've got a sub 1. That means specifically the first term in the sequence. And a sub 2 is the second term. And then I think I've got down below here a sub 15, which is the 15th term of the sequence. Now, generally we'll start our sequences at 1. Okay? However, different textbooks, and sometimes even in this textbook, they use n equals 0. If you're told about n equals 0, start at the 0 term. It's just the term before the first term. But we don't usually, we might use 0, but we don't ever use negatives in the sequence. Okay, so that's just like how you would read that notation. Okay, it will direct you to a specific term. Okay, and then rules are equations that help us find terms in a sequence. So here's where we get really mathy and where it starts to feel like algebra again. You're going to write equations that would generate the list of numbers in the sequence. Now, there are two types of rules. One type of rule is called explicit, and the other type of rule is called recursive. Our book and what we do in class, we're going to focus on explicit rules. Explicit is not like parental advisory, explicit music, naughty things. Don't get excited. Explicit here just means if I asked Mickey, here's a rule for my sequence, find me the 100th term in the rule, all Mickey has to do in an explicit rule, plug 100 in. It's just like a regular function, right? So an explicit rule will really look like functions we studied before. You just plug in the n and you get out a value, and that's the term that you want. Now, a recursive rule, the one we're not going to look at, but you might look at in Algebra 3 or in pre-calculus. Recursive rules sometimes can be really handy. They're sometimes easier to write than explicit rules, but they're harder to find terms. So, like, in order to do a recursive rule, you need the term before it to get the next term. So if I asked Mickey to give me the 100th term in a recursive rule, she would first have to know the 99th term. And to know the 99th term, she needs the 98th term, and the 97th, and the 96th. So recursive rules sometimes are helpful because they're easier to write, but if you're trying to generate values in the sequence, you'd want an explicit rule. Okay, so explicit is going to get you right to the one that you want. Okay. And then these rules are going to be like a sub n equals, and you're going to put what looks like a mathematical function behind it. It'll be in terms of n back here. So I'm actually going to go back to the previous slide. Okay. And we'll start with this first one, 2, 6, 10, 14. And let's see if we can come up with a rule for that. Okay, so let's try a rule. That's going to be some a sub n equals. And I'm hoping that someone will just shout it out instantly based on the pattern that we described. What would a lot of us just say? N plus 4. Thank you. That's what I want. Okay, now if n plus 4 is the actual explicit rule for this sequence, I should be able to plug in the different values for n and get out the numbers that are in the sequence. So that's my rule. Then a sub 1 would be 1 plus 4, which is 5.
Whoa.
Is that my rule?
No.
No. Okay. Now, what you actually wrote right there for n plus 4 is the makings of a recursive rule. It would have different notation. I'm not going to get into all of that. But if you're saying that to get to the next term, I would add 4 to the previous term, that's recursive because you need the one before it. And we want to fast track it so that we can get the 100th term really fast. So think about this. Let's say, this is crazy, no parent would ever do this. Let's say a parent agrees to pay you $4 every week that you make your bed. That's crazy. You guys all make your beds no matter what, right? $4 a week for making your bed. If you make your bed consecutively for 40 weeks, how much do your, 10 weeks, how much do your parents owe you? $40. How'd you get that?
You gave
4 times 10. I gave it away. I'm in trouble today. 4 times 10. So when you keep adding 4, repeated addition is really multiplication. So rather than saying n plus 4, we should write n times 4, which I would generally write as 4n. Okay. And then a sub 1 would be 4 times 1, which is 4. Still not the same, but I can tweak it a little bit. Minus 2. And then 4 minus 2 is 2. And if I check the second term, 4 times 2 minus 2, that's 8 minus 2, which is 6. Okay, and if I jump ahead to the fourth term, just to check the fourth term, why not? It should work for all of them. 4 times 4 minus 2, that's 16 minus 2, which is 14. So now I'm convinced this rule works. And if I now said, Mickey, give me the 100th term, yeah, 398 is the 100th term of that sequence, and I don't need the 99th term to get it. Okay, so this would be your rule for that sequence. Let's see, can you guys come up with a rule for 1/3, 1/4, 1/5, 1/6, 1/7? A sub n equals 1 over something, right? That's how you're going to generate that numerator of 1 every time. Just put a 1 in there.
110. Or, over the 1 with the denominator.
Over n plus 2.
No.
Well, if you just put n, then your first term will be 1, which my first term is 1/3.
1 over. Would you do 1
N plus 2.
1 over n plus 2. So 1 over 1 plus 2 would be 1 over 3. If I did the second term, it would be 1 over 2 plus 2, which is 1 over 4. Third term, 1 over 3 plus 2 is 1 over 5. And I've got a fifth term up here, right? This is a sub 5. So 1 over 5 plus 2 is 1 over 7. Yeah, it seems to be working out. So there's my rule for that one. Now, if you think about that one, before we were adding 4 every time, now we're adding 1 every time. So we're doing repeated multiplication or repeated addition with 1. So it's 1 times n. And then we just had to tweak it a little bit. Okay, let's write the first 5 terms of the sequence. So this, Liam, you kind of asked this question. Will I ever ask you to do more terms? I can ask all sorts of questions, but this is kind of like what you'll see in your homework. Notice this time they already gave us the rule. So now we don't have the list of numbers. We have the rule to generate the numbers. And if I want the first 5 terms in the sequence, I want a sub 1, a sub 2, a sub 3, a sub 4, a sub 5. So I'm just plugging in those numbers for n. So a sub 1 is 3 times 1 minus 2, which is 1. A sub 2 is 3 times 2 minus 2, which is 4. A sub 3 is 3 times 3 minus 2, which is 7. Oops, you might at this point realize a pattern. What's happening every time?
It's going up by 3.
It's going up by 3, which makes sense because it's 3 times n, right? So that means that you keep going up by 3. So now I know a sub 4 is 10 and a sub 5 is 13. So you might write it out, or like in this one, can you get the first 5 terms just plugging it in your head? 1 squared minus 1 is 0. 2 squared minus 1 is 3. 3 squared minus 1 is 8. 15, 24. And then, like this one, maybe with the factorial, I just threw that in there since we finished our chapter 10. Maybe this one you'd be better off writing some things out, right? So what's 1 factorial? 1. So the first term is 1/2. What's 2 factorial? 2 factorial. So 2 over 2 is, 1. What's 3 factorial? 6. Because it's 3 times 2 times 1. So 6 over 2 is 3. Then what's 4 factorial? 24. You're taking 6 times 4 now. So that's 24 over 2, which is 12. And then what's 5 factorial? 120 divided by 2. That gives me 60. So 1/2, 1, 3, 12, 60. Now, I'm going to make a quick note here about graphing sequences. Now, think about graphing sequences, like putting them on a graph, like you're graphing a function. So if we go back to function notation, f of x was a fancy way to write y. So in sequence notation, a sub n, the terms of the sequence are like your y values. What are you plugging in? In function notation, you're plugging in x, so that's your input. What are you plugging in sequences? N's. So the numbered term that it is your input. So that's going to look like if I were to graph, I'm going to use this first sequence we did. What is that? 1, 4, 7, 10, 13. Okay, if I were to graph that sequence, I would put n on the horizontal. A sub n would be on the vertical. Well, for n's, I'm talking about the numbered terms. First, second, third, fourth, fifth. So I want to have 1, 2, 3, 4, and 5. And then I need to go from 1 to 13, so on this one I'm going to go by 2's. And then I'll just plot my points. Here, my n value, so these are my a sub n's. my n values are 1, 2, 3, 4, and 5. So I would have 1, 1, 2, 4, 3, 7, 4, 10, and 5, 13 would be somewhere up there. 1, 1, 2, 4, 3, 7. Now, one thing that would be a big difference from other functions we've graphed, I'm not going to connect the dots. Why not? Why are they unconnected? Yeah, the word we use is in math, we call it discrete. And discrete means not continuous. And the reason why it's not continuous is if you draw a line connecting all those dots, you're saying that there's some 1.5 something. Is there a 1.5 term? No, there's a first term, second term, third term, fourth term. So by definition, sequences are discrete. So they'll be unconnected. What do you notice about if you were to connect these dots, what shape would it form?
Straight line.
This one would be looking like a line. Not all sequences would look like a line, but you're going to be asked questions about graphs of sequences. This one would look like a line. And look at the rule for that one. What does 3n minus 2 look like? A linear function, mx plus b. So that 3 is like my slope. I keep going up by 3, so it's my constant slope. And negative 2 would have been my y-intercept. If I graph a sub 0, it's down at negative 2 on the y-axis. So just some things to think about in terms of sequences. Okay. Your homework assignment is on your gold sheet. We've got about 5 minutes left, so I'm going to be passing back your test from, what was that, Friday before break. I'll put up some of the 5 and 8 if you want to get started on those while I'm passing things back. So here you could get 5 and 8 done, right? The first 6 terms of the sequence.